chemists. This lecture is going to be about solutions and how polarity, solubility, temperature, pressure all affect the ability of two different chemicals to mix together. So let's start by defining some terms, and I'll start with a solution you've probably made at some point, like a Kool-Aid solution or a sugar solution. So you take a cup of water, there's your water, and you're going to take a packet of Kool-Aid, you're going to dump Kool-Aid particles into the water where they dissolve, and then you're going to drink it, obviously. So we have the water itself. We're going to have terms for all this. So new term for the water, we will call this the solvent. All right, and then the particles that we're dumping into the water will be the solute. All right, just fancy chemistry words for things you probably already knew. You'll mix it up together, and when everything is dissolved together, and let's say it has some like red color or blue color, depending which Kool-Aid you like, and the particles are all kind of uniformly spread out and mixed in, although you wouldn't see them, obviously, in a final solution, this would be all together the solution. So the solution consists of solute particles dissolved in a solvent, which is sometimes called the medium for which they dissolve into. And we're going to be exploring a lot of different ways that a lot of different aspects of solution, and we're going to start with what causes those chemicals to mix in the first place. So let's do a real easy solution that, well, we can use the, let's do a salt solution first. So one thing you've probably noticed, if you ever had table salt, right? There's a shaker of table salt, a bunch of little, there you go. Pretend there's salt crystals all the way up the side. Something like that. And that shaker of table salt, you're going to pour into a glass of water, and it dissolves really well. You can put a lot of salt into water, and it makes a pretty easy solution. So we kind of talked about this in previous chapters, but table salt, sodium chloride, is a bunch of positive ions and a bunch of negative ions, and they form this sort of crystal lattice. So if you were to look down deep at what's inside of there, you would see a bunch of sodiums surrounding each chloride and a bunch of chlorides surrounding each sodium, like that. And they're all being held together by this electrostatic force because they're positively and negatively charged. Well, if we look at the water molecules, and again, we've seen this in previous chapters, the bonding chapter, we know water is a bent structure because of its two lone pairs. And because oxygen is more electronegative than hydrogen, we know that oxygen will receive a partial negative charge on that end, and the hydrogens will receive a partial positive charge on their end. And so just kind of like the sodium chloride, because there's a separation of charge going on, these two types of chemicals mix really well. So if I were to make a sodium chloride solution, let's draw a big beaker so we can kind of look inside, what I would see is I would see the water molecules like this with all the, remember this is the negative end of the water and this is the positive end of the water, and all of the positive ions, the sodium ions, would be up here next to that negative end, and all the chloride ions would be down here next to that positive end. Because water is very polar, ions dissolve in it very easily, and so this would be my solution. So the more polar a solvent is, now we're getting into our original terms, water being a very polar solvent, ionic solutes dissolve very well into water. As opposed to something like, you may have this in your fridge, an old salad dressing bottle, right? Here I'm thinking specifically of Italian dressing. Italian dressing, among other things, usually has in it, usually contains this chemical, which is vinegar. All right. And it usually contains also a lot of water. So there's water is probably a big portion as well. But there's also a lot of oil, and oils, I won't draw the whole thing out, but oils are really long carbon chains, hydrogen molecules on them. for the most part. Something like this. And so if you look at an old bottle, I don't mean like an old, like it was made years ago. I mean like a bottle you've left in there for a while. What you will find is that there are two layers. You'll see like a separation between the water layer and the oil layer. They don't mix very well, not like the salt did with the water. And the main reason is that this is a nonpolar liquid, and this is a very polar liquid. Now, if we're looking for the vinegar, vinegar sort of has this little nonpolar end, but it has a very polar end on this side. And the vinegar is going to be dissolved probably more in the water than it is in the oil. So if I was looking through let's say this is the water on top, and this is the oil on bottom, then if I tasted the water, I'd probably taste that vinegar taste more in the water than if I tasted the oil, I don't think. Because this guy being more polar would be likely to dissolve in the polar solvent and not likely to dissolve in the non-polar solvent. So this is almost like there's two solvents in this case. And if I dump salt in there, the salt is more readily going to dissolve in the water layer than in the oil layer, if that makes sense. Okay, so in general terms, if we're going to make a rule about this, chemists tend to say like dissolves like. So if I spilled all over my table while I was cooking, if I spilled a bunch of salt on the table, one very quick way to clean it up would be to get some water on a rag and wipe it up, because the salt would dissolve in the water as I was trying to wipe it up. If I spilled oil on the surface of my table, it would be not a good idea to reach for the water, because water and oil are polar and nonpolar. They're not going to mix very well. Okay, so how do we clean up oil? So we have this stuff, soap, right? You are familiar with this, I'm sure, by now. But you may not have seen the structure of a soap molecule. Soap picks up oil, and yet you can also wash it off your hands with water, right? Soap doesn't stay on your hands under running water. It seems to dissolve in both things. Why? Well, let's draw a soap molecule. A soap molecule has a really long oily end full of a bunch of carbons, and then at the very edge it has a little polar end with an oxygen on it. So if I kept doing this, I would have a bunch of hydrogens, like so. Big, oily, non-polar end, and a little tiny polar end. All right. Sometimes they'll draw a soap molecule. I'll draw a simplified version. It's like a big, long tail with a little OH at the end. And so if I have oil on the table, here's my oil molecule up here. Which is perfectly nonpolar. And then this soap molecule, the nonpolar end, can stick to the oil end and they can dissolve together. But the polar end, the OH end, can stick to the water molecule because they dissolve together. All right, and that's kind of how it works there. And so you can clean up both, right? This is how we get rid of oils using water. Is you got to have this intermediate soap molecule that's kind of a bit of both. Okay, let's keep going.